Hello friends, in this video we are going to discuss about Fraunhoffer diffraction. Before we start, please do subscribe the channel, hit the thumbs up button. Also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. So now let's start. So here you see, suppose we have a slit and a parallel beam of light is allowed to pass through, and that means you can say that a plane wavefront is allowed to incident on this slit, right? And the ray of, when you draw a plane wavefront, then we used to draw the light rays in the direction perpendicular to the wavefront, right? So hope you know these things. So now you see, if you put a screen here, you will see the light not only on this portion, but here you will see the light out of this region also. And here you see this width of this region is same as the width of this slit. So we used to get the we used to observe the light in this region, but we will observe light on beyond this region as well. Okay, here also and here also, right? So hope you have understood this. This is because of diffraction, right? This is because of diffraction. Now you see, again, this light beam of light is allowed to pass through the slit. Then here you will observe a pattern of bright, dark, then again bright, then again dark, again bright, right? On both sides, not only at the center, upper part of the center, in lower part as well. Then bright, again dark, then again bright, and so on, right? And this will be called central maxima, and brightness of the remaining maxima will be decreasing when you go up and down, right? Now you see here this bright fringes, this central bright fringes, when we will get bright fringe. Suppose we get here at this point, when two waves superpose, then if they are in the same phase, then we will get here bright, and if they are out of phase like this, okay, then you can say these two cancel each other, then here you're gonna get dark fringe. Okay, so you can just to visualization, just I have said like that. So hope you understood this. So at this point here you're gonna get dark fringe. Okay, if they are out of phase, if the waves are out of phase at that point, right? Now you see, here we're gonna get bright because you see the light, so here we have used concave lens to focus, as you can see in this diagram, to focus this parallel light. These are straight, okay, these are the straight parallel light, and those are focused at this point P. Okay, and as here you see, this is the midpoint of the slit O, and here you see these 2 points are equidistant from this midpoint, and that's why the light from these 2 points travels same distance when they reach the point P. So that's why path difference between them is 0, and this is the point of maximum intensity, right? This is the point of maximum intensity. Suppose we have considered another point P dash, as here you can see this point. If we assume we have taken another point P dash, that will be point of maximum or minimum. That depends on the path difference between the light. Suppose light will be will be traveling in this direction as well, not only straight in the straight direction parallel to OP, will be also in the direction inclined to OP. Light will be also traveling in the direction inclined to OP as well, in this way. Okay, and this point will be point of maximum or minimum. That means it will be bright or dark. That will depend on these two secondary waves. Okay, depend on the path difference of these two secondary waves. Okay, and this is the figure. Okay, so hope you have understood this. So here you see, here we have considered, here you can see these rays of light. See the diagram, these rays of light, these are going parallel to this line OP, right? And these are secondary waves, because this is the wavefront. This is the wavefront. This is wavefront. Okay, this is plane wavefront incident on this slit, and then here you see each point, according to Huygens principle, each point on this wavefront will act like a secondary wavefront, secondary source of source of secondary wave. Okay, that means this is the wavefront, and if this point, each point on this wavefront act like secondary source of secondary waves, then from here also wavefront will be emitted like this, and from this point also wavefront will be emitted like this. And here you see, you can see the superposition of light. Okay, due to which we get the dark and bright fringes, and where we will get the waves in the same phase, there we're gonna get the bright, and if we get the waves that overlap each other but out of phase, here at that point we're gonna get the dark fringe, right? Hope you have understood this. So here you see, this is the diffracted light, and we have taken these two in the direction which is at an angle theta with this straight direction, with this OP. These secondary waves are in the direction, these diffracted waves are in the direction at an angle theta with this OP, right? Hope you have understood this. And this point of P will be point of means maximum or minimum. That will depend on the path difference between these two light, that is originating from the point A and B. Okay, so hope you have understood this. And here you can see that clearly in this diagram, since these lights which are going parallel, this one, so let me show in red color, this one and this one. Here you see these 2 points are equidistant from O. That's why these two lights covers equal distance, so path difference will be 0. But here you see this light, let me draw in black, this light, you can say this one which is at an angle theta, and this one, these two parallel ray. Here you can see, let me make it 1, let me number it 2. Okay, so this second ray, second wave, here you can see this is 1, this is 2, this number 2 is traveling longer distance compared to 1, and the path difference between these two light is given by BL, where AL is the perpendicular on this secondary wave, right? Hope you have understood this. And this is the A is the width of this slit. This slit is of width A. Okay, so hope you have understood this. Now let me write what I have considered here. So here is the slit. These are the beam of light. These are the rays of light and incident on this slit and then focused by this lens at the point P. Okay, and these are the diffracted rays at an angle theta, and those are focused at P dash. So here you can see this is AB, slit AB. Okay, and this O is the midpoint between the AB, and this is A, width of the slit is A. Okay, right? Okay, Now you see the angle made by the secondary wave which is diffracted, okay, and focus at P dash is angle theta with the rays which are parallel to OP, okay, and this is the perpendicular AL. Suppose AL is the perpendicular, and this angle will be also theta, angle between AB and AL, because I will explain what is the reason behind it. Let me write what I have considered. This is, suppose this distance between P and P dash is suppose x. Suppose, let me write that, okay, a plane wave front incident on the slit AB, and each point on this wave front will be regarded as a source of secondary wave, right, according to Huygens principle. And the secondary waves traveling in the direction parallel to OP come to focus at P, and the secondary waves from the point P, from the points equidistant from the O, from the center O of the center of the slit O, are and situated in upper and lower halves. That means you can take the point A and B. From these 2 points we have 2 waves, secondary waves, that focused at P, right? As they okay, as they are traveling, as they travel the same distance, okay, as they travel the same distance, there will be no path difference. That means path difference will be 0. So that's why this point P, right, that point P will be the point of maximum intensity, right? Here we're gonna get the central bright fringe, actually maximum intensity, right? So hope you have understood this. Now you see, let me explain why it is theta. Here you see, you can see that this is straight, right, and this is the diffracted secondary wave, okay, and angle between these two is theta. Now this AB is perpendicular to this straight ray of light, and this AL is perpendicular to the diffracted light. So that means we have got this situation. This is a straight which is parallel to OP, and this is the light which is inclined at an angle theta on it. And if you have 2 lines, an angle between them is theta, and if you draw 2 perpendiculars on these 2 lines, then the angle between these 2 perpendiculars will be also theta, right? So remember that this is simple geometry, right? So now here you see, let me write the secondary wave, just traveling in the direction in which make an angle theta with OP, reach the point P dash on the screen, okay. The point P dash will be maximum or minimum, point of maximum or minimum intensity. That will depend on the path difference between the diffracted light from the point A and B, okay. So hope you have understood this. Let me go back to the previous slide. So here you see, let me copy this diagram and let me go to the new slide. Here, let me copy this diagram. So I'm going to use the diagram again. So here is the diagram. Here you can see, this is the diagram, okay. Now you see here, now okay, let us consider a triangle ABL. This triangle, you can see ABL, this is ABL, this triangle. Here you can see, from triangle ABL. So what we're gonna get, this is AB, and this is the perpendicular L. So this BL gives the path difference between these two waves, this one and this one, right? Hope you have understood this. Okay, it gives the path difference between AQ dash and BR dash. You can consider that way. Let me consider this point is Q, this point is Q, and this point is R. Okay, so AQ dash and BR dash. Okay, here we're gonna get the path difference from this triangle, and that is BL. Okay, so let me clean this. Okay, now you see path difference is BL. So how to obtain this? We know this angle is theta, right? This angle is theta, and length of this AB, that is the width of the slit, this is small a, right? We have considered that the width of the slit is small a. So let small a is the width of the slit. Let me write that. Okay, then from here sin theta, we're gonna get BL by AB, perpendicular by hypotenuse, and AB is equal to small a. So here we're gonna get BL is equal to small a sin theta, right? That is the path difference. Now you see, if two waves are focused at this point P dash, okay, now they are coming from these 2 points, suppose A and B. Okay, here though we have drawn two waves, actually not only two waves, large number of waves are going, large number of waves are focused at the point. Okay, now you see, if the path difference between this one and this one, okay, is lambda, that means they are in phase. Actually, if this is a wave and this is a wave, suppose, and this is lambda, there is another wave, and the path difference between these two waves is this is lambda. In that case, they are in phase. But here you see, when you take when you see the path difference between the two waves going originating from A and B is lambda, then path difference between the ray of light, or between the wave that originating from O and A, that path difference will be lambda by 2. Then these two will be out of phase. In that case, here we're gonna get dark. So you can consider that suppose from here we 50 waves are originating, from here 50 are originating. Okay, so in that case, here you see, let me take a new slide to explain. So suppose this is the wave front, and this is the point A, this is the point B. Okay, this is the point P dash. Okay, and this is the lens, and this is the diffracted, these two are the diffracted rays, waves, secondary waves that focused at P. Now if you consider 50 on this side and 50 on this side, okay, if the path difference between this one and between the 1 and 100 waves is lambda, then the path difference between the first and the 50th will be lambda by 2, and these two will be out of phase at this point. Similarly, the path difference between the second wave, the second one, and the path difference between the 51st one, those two will be also differ by lambda by 2. Again these two will be also out of phase, and so on, right? That's why in that case we're gonna get dark when the light waves originating from A and B are traveling to different distances, differ by the wavelength lambda, right? Hope you have understood this. If the path difference between this one and this one is lambda, then path difference between this one and this one will be lambda by 2, right? Hope you have understood this. In that case, now coming back to original slide, here you see, so we can say that so that means we're gonna get the bright fringe if we're gonna get the dark fringe if the path difference between the waves originating from A and from B is lambda. Either lambda, it may be 2 lambda, it may be 3 lambda, and so on. Okay, so not only lambda. Okay, that means integral multiple of lambda for bright fringe. So this BL must be equal to lambda, right? And that means lambda, not only lambda, integral multiple of lambda, it may be 1 lambda, 2 lambda, 3 lambda, and so on, right? And for the bright fringe, it must be odd multiple of lambda, that is 2n plus 1 by odd multiple of lambda by 2. Okay, odd multiple of lambda by 2, because you cannot take even multiple of lambda by 2, then it's gonna be again even multiple of lambda, right? So hope you have understood this. When you take path difference between this the topmost and the lowest one, then if you take path difference suppose 3 lambda by 2, right? 3 lambda by 2. Let me explain in a different slide. Let me take another slide. Here you see, suppose this is the slit and this is the lens. These are the diffracted rays focused at the point P dash. Okay, focused at the point P dash. Now, as I have already explained, if the difference, path difference between this one and this one becomes lambda, in that case path difference between this one and the originating from this one becomes lambda by 2. Then there will be, these two waves will be out of phase. Then we're gonna get at P dash dark fringe. So if you take, suppose you have taken here 3 lambda by 2, suppose, then these two will be out of phase. These two will be out of phase like this, right? And if these two are, this one and this one are out of phase, then this is going from A, this is going from B, and the waves going from the midpoint between from this point, which is midpoint between A and B, that will be in phase with the light that is originating from A. So then here we're gonna get the bright one, right? And similarly, this wave going from B will be in phase with the light below this one, in phase with this, right? So hope you have understood this. So now you see, so that means simply you can say, when these are the 2 points A and B, when these two waves are in phase, okay, in phase. So this is the number 1, this is the number 2, number 100. Suppose this is point A, this is B. When first and the 100, these two waves are in phase, okay, these two waves are in phase. I have drawn two waves, these are in phase. Then the number 1 and the 50, these two are in out of phase, okay, these two are in out of phase like this. because when the difference between these two is lambda, then here difference between this one and this one will be lambda by 2. If the path difference is lambda by 2, then obviously if this is at this position, another will be at this position, right? And they are out of phase. In that case, we're gonna get. So then we can say that similarly, if these two are out of phase, these two waves are out of phase like this. This one and this one, these are out of phase like this. This one and this one. Then if this one and this one are out of phase, then this 50th one will be in the phase with the light originating from 1. Similarly, this 51st one will be in phase with this, right? So that's why we're gonna get here bright fringe when these two are out of phase, and these two will be out of phase when we will take odd multiple of lambda by 2, right? Hope you have understood this. Now let me go back to the slide. So now let me clean these things and let me write what I have explained now. For minimum intensity, this BL must be equal to n into lambda, where n is equal to 1, 2, 3, so on, right? And BL is nothing but A sine theta n lambda, and from here we can say that sine theta is equal to n lambda by A. That's what we can say, right? So we have understood this. Now you see, for the maximum intensity, let me take a new slide. For maximum intensity, this BL path difference should be equal to 2n plus 1 into lambda by 2. I have already explained why, right? And this BL is nothing but A sine theta, so 2n plus 1 lambda by 2, right? And from here we're gonna get sine theta is equal to 2n plus 1 into lambda by 2 A, right? That's what we have got, right? So hope you have understood this. Now let me go back to the previous slides. So let me take this L, let me name the lens L. Okay, this is lens L, this is the lens L, suppose. Okay, now you see, let me show you something. Now you see, this is the slit, right? This is the slit AB, and this is the lens L, right? And this is the screen. So this point is P dash and this point is P, and distance between them is X, right? Now you see, let me show you something. This point is O, P, this is O. Now you see, this light is focused at P dash because of this lens L. So when you consider this lens is very close to this slit, or you can consider if you consider the screen it is very far away from the slit, in that case you can consider this length as focal length, okay, of the lens, because this light is focused at P dash by this lens only, right? So here you can see this is the perpendicular, which is X, this is the hypotenuse, and you can say that for this condition sine theta is equal to X by F, right? So we can write that, so if the lens L is very close to the slit, or the screen is far away from the lens, not slit, sorry, lens, So in that case we can write that sine theta is equal to x by f. Okay, now you see that suppose this is the central maxima, this is the central maxima, so this is the central maxima, and then here you see, then we have got the, suppose, dark fringe, this is the dark and this is the dark, right? This is the position of the dark. Now you see how to obtain the width of this central maxima, right? So here you see from this and this is the position, this is the position of the first secondary minima, right? P dash. In that case, if you go to the condition for minima, here is the condition, right? Okay, for n is equal to 1, we're going to get sine theta is equal to lambda by a, right? That's what we're going to get. Okay, now you see here we can replace this sine theta by this value, right? So then what we're gonna have, we're gonna have this next step is lambda by a is equal to x by f, right? So from this condition, right? So hope you have understood this. So at P we had got the central maxima. At P dash we have got the P dash will be the dark fringe, first dark fringe, if this sine theta equal to lambda by a. This is the condition. From this condition we have got that the first dark fringe after the central bright will be obtained at P if this condition is satisfied for n is equal to 1, right? So hope you have understood this. Now we can use this. Okay, now width of this P, if we take the dark on both the sides, okay, and distance between P and P dash is x. So here similarly the first dark below P will be also x distance away from P, so this width is twice x, right? So hope you have understood this. So here we're gonna write since P dash is the position of first dark fringe if P dash is the position of the first dark fringe, then sine theta must be equal to lambda by a, right? So hope you have understood this. Now let me clean this figure. Okay, so let me divide the base so I can do here the remaining part. So from this step what we have got x is equal to lambda f by a, so width of the central maxima, therefore width of the central maximum is, let me write w, twice x, that is equal to lambda f by a, right? So hope you have understood this. Now we are going to use the calculus method here to discuss the intensity distribution. Now let us consider a very small element del dz of the wave front. So here you see this is the wave front, you can see this point is A, this is B, okay, and this is the slit, here is the incident wave front. So let me draw it again. So now you see this is the wave front, okay, and let me consider a very small element dz, okay, on this wave front, right, a very small element dz, and the width of the slit we know that is a, right. So this point is a, this point is b. Now you see this is the midpoint of AB, O, center of the slit, right. Just give me a second. This is the screen and here is the point P, and this is the point P dash. So from DZ, the distance from DZ to P is supposed, let me take this row, and the distance from this center O to P dash is suppose small r. Let me take this r, okay, and this angle is theta. We know this angle, I am talking about this angle, right. So, and the distance between the center O and dz, this element, is suppose z from the origin. Let me draw the diagram, let me make the diagram large, okay. So here is the slit AB, okay, this is the wave front, okay. We have taken a very small element dz, and this is, you know, at a distance z from this O. So let us consider the coordinate of this is 0 comma z, okay, this distance is z. Now here is the point P and here is the point P dash. Again let me take this distance of dz to P dash is rho, and distance from the origin to P dash is r, and this angle is theta. So hope it is clear now, okay. Now here you see, let me consider this distance is x naught, this distance is x naught. So, and this distance here you can see, let me consider this distance is suppose z naught, so that the coordinate of this point x naught comma z naught, okay. Earlier we had considered distance between P dash, so you can make it z naught if you want, okay. So let me change in previous slides also, wherever you have seen x, make it z naught, okay, otherwise it will be very confusing for you, I think, okay. Let's make it z naught, right. So here let me change the x by z naught. Let me go to the previous slide. So here let's make it z naught, okay, so that I can write its coordinate as x naught comma z naught, okay, and x naught is the distance from the slit to the screen, suppose, okay. So hope you have understood this. So then the coordinate of this P dash we can write x naught comma z naught, right, considering this O as origin, right. So hope you have understood this. So now let's get back to the point. So here I have taken this way, okay. Now you see, you know the wave equation, the displacement equation of a wave. You know, suppose we have a simple harmonic wave. This is the origin O. So in this case we know that displacement of a particle, this is a particle which is at a position x, and its displacement y at time t is given by this equation, that is y is equal to a sine omega t minus phi, right, where phi is the phase difference, and this here you see omega is the angular frequency and a is the amplitude. You know these things. Now here you see we have considered this small portion, okay. In this case the resultant displacement, so from this portion not only one wave will travel to this point P, okay, more than one waves will be traveling towards P. So resultant displacement at this p dash, not p, sorry, p dash, due to this element will be given by, let me consider instead of y, let me consider dy, okay, k dz sine, here you see omega can be written as 2 pi by t, right? 2 pi by t is the time period, hope you know this. Then here we can write 2 pi by capital T, then we have small t, then phi is the phase difference, right? Phi is the phase difference here. Now you can see that when the path difference is lambda, so hope you know this things. When the path difference is lambda means equal to wavelength, okay? If you have path difference equal to wavelength, then this is the path difference, then the phase will be, this is half cycle pi, this another half cycle 2 pi, right? Total 2 pi. So for a distance equal to lambda, so we get phase difference 2 pi, and for 1 unit it's gonna be 2 pi by lambda. And if we have a distance rho, here you can see, then the phase difference between the point that is at this coordinate o comma z and at this point p, phase difference between at these 2 points will be given by, for distance rho it will be given by rho into 2 pi by lambda. Hope you have understood this. If the distance between this point, this p dash, and the point on dz is equal to lambda, only, in that case phase difference should be 2 pi. Now here the distance is rho, so that's why first we have found the if the path difference is unit, then phase difference is 2 pi by lambda. So that's why for path difference rho, phase difference will be rho into 2 pi by lambda, right? So here instead of writing phi, instead of phi we can write 2 pi rho by lambda. So that's why this equation becomes 2 pi rho by lambda. That's what we can write. Now let me clean these things. Sorry, just give me a second, just wait. Okay, so now you see, so what we have got, sorry, just okay, so this is nothing but the displacement at the point p dash due to the element dz at any instant t is given by this equation, right? So now you see we can take 2 pi common, right? So then this equation will be of this form: k dz sine 2 pi, here we're going to get small t by capital T minus rho by lambda. That's what we're going to have. Now you see, let me tell you one more thing. Let me clean this diagram. Okay, so let me mention what I have considered here. Okay, so let us consider, before you write this part, first write what you have considered. Let us consider a small element dz on the wavefront dz of the wavefront with coordinates, with the coordinates 0, 0, z. I am talking about this element, right? And the coordinates of the point, the coordinates of the point P dash are x naught comma z naught, this point, right? Here you can see. Okay, then write this part. Okay, and this diagram must be drawn. Okay, now let us take, this is suppose equation number 1. This is suppose equation number 1. Now you see, you must be confused about this term what I have written. This is nothing but the resultant amplitude at this point P dash due to the waves, superposition of waves coming out from this dz component, right? So from this element dz, so more than one waves are going to that point P dash, and due to the superposition of this waves, there must be a resultant amplitude, and this amplitude is directly proportional to this element dz. So to make it equal, we need a constant. That constant is k, right? So hope you have understood this. So now here you see, this is the equation. Now in order to obtain the resultant displacement at this point P dash due to this whole wavefront, due to this complete wavefront from A to B, we need to integrate this equation. We need to integrate this equation dy, then k dz, let me write the dz here, then sine 2 pi t by capital T minus rho by lambda. So we need to integrate this. Okay, we need to integrate this from minus a by 2 to plus a by 2. Let me explain why. Because here you see, this is a, and the lower the part below the O is minus a by 2, and above O we're gonna get a by 2 plus a by 2. So we will consider this O is the origin of a coordinate Cartesian coordinate system, x axis, y axis, like this. This is y dash, this is x dash. In that case, you see, if the width of this slit, so here you see, this is the slit A, B, this is the O, and width of the slit is A, then upper part and lower part both a by 2, right? A by 2. So this upper part will be considered as positive and the lower part will be considered as negative. Below origin negative, below and above the origin positive, right? Hope you have understood. This part is negative, this part is negative a by 2, and this part is positive a by 2, right? Hope you have understood this. So now let me cut this step and let me write in a new slide properly. So first let me add a sentence here. The resultant displacement, at P dash due to the whole wavefront, can be obtained by integrating this above equation number 1. So let me show you in the next let me copy this equation number 1. Let me take a new slide. Okay, so here is the equation number 1. this is displacement at p dash due to the element dz only, and due to the whole wave front we will obtain by integrating it, right? So then let me rearrange the terms. Let me write the dz here. Okay, so we can write this one. So we're going to integrate it from minus a by 2 to plus a by 2, plus a by 2. Here it's gonna be 0 to y, right? Hope you have understood this. So if we integrate this, then what we're gonna have here, dy will be equal to y. Let me, for the time being, let me keep the right hand side as it is. Okay, like this only, right? Just let me keep this way. Okay, now, okay, this is suppose equation number 2. This is suppose equation number 2. Now you see, let me go back to the previous slide. Now let me copy this diagram so that I can explain. Let me copy this diagram and let me take go to new slide. So here is the diagram. Let me make it smaller a little bit. Okay, so here is the diagram, right? This was the diagram. So this is supposed to be z naught, right? So now you see, from this we can write rho square, this is rho square x naught square is equal to, here you see this point. If you draw a line here, so this gap is z, right? This gap is z. Actually, here let me show you. This is the element, suppose dz, and distance from this element to p dash is rho, and to the screen it is x naught. Okay, and the distance from the origin to this dz is z, right? And from this line, the distance from p to p dash is z naught, and here you see, as dz is at a distance of z from o, that's why this gap is z. So that's why this part, this remaining part, here you can see this remaining part of this triangle, that must be z naught minus z, right? So we got a triangle. Here we have the element dz, and this is x naught, this is z naught minus z, right? And this is rho. And from this triangle, what we're gonna get? We're gonna get that rho square is equal to x naught square plus z minus z naught whole square, right? Hope you have understood this. So let me explain it again. Let me go to previous slide. Here you can see this distance, this is x naught, right? And if we draw a line here, this gap is z, because this coordinate is 0 comma z. That means the distance between this element dz and the distance between this point o is z, right? Hope you have understood this. This part is z. So that's why this portion must be z naught minus z, because this distance from p to p dash is z naught, and this portion is z. So this remaining portion must be z naught minus z, right? So from this triangle, from this triangle, what we have got? This is rho hypotenuse, and this is x naught, and this part is perpendicular is z minus z naught. So using Pythagoras theorem, we have got this equation, right? So hope you have understood this. Now let me make it clean. Okay, just give me a second, just wait. So sorry. Okay, so that you can understand. Okay, let me make it more clear. Okay, so this is the diagram. right? Now what we are going to do, let me go to next slide here. From here let's find here one more thing. We have considered this distance is r, from O to P dash. We have already considered that, right? OP dash is equal to r. Let's mention that one as well. Now from this triangle, this part is z naught. From this triangle, what we can write? This is x naught. We can write r square is equal to x naught square plus z naught square, right? We can write that. Hope you have understood this. So now here what we're going to write, x square is equal to, sorry, r square is equal to, this is r square is equal to x naught square plus z naught square, right? So x naught square plus z naught square. So that's what we have got. Now from here we can write x naught square is equal to r square minus z naught square, r square minus z naught square. Now here you see, so if we substitute this value x naught in the above equation, okay, in this equation, suppose this is equation number 3 and this is suppose equation number 4, using 4 in 3. If we use 4 in 3 using equation number 4 in 3, what we're going to have, rho square is equal to, instead of x naught we're going to write r square minus z naught square, on the other side plus z minus z naught, sorry, z naught minus z whole square. That's what we're going to have. And from here what we can do, let's just now let's expand this. If we expand this, then what we're going to get, r square minus z naught square, r square minus z naught square. Let me write it properly, okay? Then, and if you expand this using a minus b whole square formula, then you're gonna get z naught minus z naught square minus 2 z naught into z plus z square. So here you can see clearly that these two are cancelled. Now if you take r square common, then rho square gonna be equal to r square. On taking r square common, here we're gonna get 1, then minus 2 z naught by z naught z by r square plus z square by r square. That's what we're gonna have, right? Now you see this r square is very greater than z. Now let me go back to the figure. Here you see this distance r square. Here you can see, let me make it red. This distance r is greater than z, very greater than z. Okay, so compared to z, r is very greater than z, because we are considering this screen is at a very significant distance from this screen, okay, which is comparatively very large than z, okay. So in that case, so that means we have considered that this way, that this is the slit and this is the midpoint between a and b, and we have considered that element dz which is very close to o, okay. This dz element is very close to o, so that this distance z is very small compared to the this distance r, okay. This distance r from O to P dash, okay. So that's why we can consider that we can say that r is very greater than z, and if r is very greater than z, we can neglect this term r square by z, right? Hope you have understood this. Now let me clean this and let me take my slide, sorry, here. So let us neglect this term, okay. So then what we're gonna get, so neglecting r square by z square, since I made it reverse, so z square by r square. Okay, since r is very greater than z, we get what we get. If you neglect this term, you're gonna get rho square. Let me copy this, just give me a second. So you're gonna get this rho square equal to r square 1 minus 2z not z by r square, because this last term z square by r square is neglected. This term is neglected, right? Hope you have understood this. So this is what we have got. Okay, now here you see, taking square root, we're gonna get rho, then here it's gonna be r 1 minus 2z z naught z by 2 z naught z by r square. Here we're gonna get half on taking square root, right? Power is half. So let me write it properly. Now you see, if you expand 1 minus x whole to the power n, then it will be equal to 1 minus nx plus n into n minus 1 by factorial 2 x square. So here actually we have factorial 1. Factorial 1 is 1, that's why we don't use to write that. Then plus dot 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 so on, and next term will be n into n minus 1 into n minus 2 x to the power 3. That's how we're gonna get. So if we apply this formula here, then what we're gonna get? We're gonna get 1 minus half into, instead of x, consider this part as x and compare with this, and n is taken as half, right? Then what we're gonna have, half into x is here 2z naught z by r square. That's what we're gonna have. And in the next term we're gonna get half into half minus 1 by 2 factorial, then 2z naught z by r square whole square. Here this using the higher power of this term will be neglected. Okay, this is gonna be very small, so this part is neglected. So we're gonna take only this term. So here 2 cancels, so we're gonna get rho r 1 minus 2 z naught z by r square. Okay, that's what we have got. So using binomial theorem and neglecting higher powers, of 2 let me write z naught z by r square. Okay, neglecting the higher power of this term, right? Hope you have understood this. Okay, so let me write this within bracket. Now r into 1, that's going to be r, and r multiplied with this, then r square will be cancelled with r. So we're going to get z naught z by r, right? That's what we have got. Okay, this is the value of rho. Now from the triangle OP', okay, from this triangle, so here you see, let me draw the diagram here again clearly. First let me clean these things. Just wait. Okay. So now you see, this is the element z and its coordinates are 0 z, not z, not z, and the coordinate of p is x naught z naught, and distance from this element is rho to this p dash, and distance from the origin is r to this same point p dash. Okay, So now from this triangle O, P dash and P, this angle is theta, right? From this triangle, what we can say, from triangle O, P dash P, we can say we will get sine theta is equal to that Z naught, that is the perpendicular Z naught by hypotenuse R, Z naught by R, right? That's what we can write. So that's why what we can do now, that it implies Z naught is equal to R sine theta, right? Now let's replace this Z naught by this value R sine theta. Therefore what we're gonna get, rho is equal to R minus, instead of Z naught if you put R sine theta, then into again Z by R. So here this is replaced by this value which is within the bracket. So this R cancel, so that's going to be equal to R minus Z sine theta. That's what we have got, that is the value of rho. So let it be equation number, so what was the last equation number? Equation number 4, right? Now let it be equation number 5. Now let me use this equation number 5 in equation number 2 here in this equation. Okay, let me use here, this is the rho, right? So let me use here using this equation number 5 in 2. So that means here we're going to replace this rho by this value, that R minus Z sine theta, R minus Z sine theta, because we have got this rho is equal to R minus Z sine theta. So that's why this point, this rho will be replaced by this value. So then what we're gonna get, so let me copy this equation number 2. Okay, now let me take a new slide. This is the equation number 2 and here is the equation number 5. Okay, this is the equation number 5, this is equal to rho. So now let's put this one here. Then what we're gonna get, using 5 in 2, then y is equal to k integration minus a by 2 to plus a by 2 sine 2 pi within bracket small t by capital T minus, and here instead of rho we're gonna write R minus Z sine theta divided by lambda, then bracket close dz. That's what we have got. Okay, if we replace this rho by this value, this is the value of rho. Okay, so now let me clean the things, just wait. Okay, that's what we have got, right? Now okay, let me simplify this. So what you can have after simplification, k, then integration minus half a plus half a, then sine 2 pi small t by capital T minus r by lambda, then minus z sine theta, z sine theta by lambda dz. So now if we integrate it, now you see here we have dz. So if we integrate with respect to z, so this part is only the function of z, this part involves z only, these terms will be regarded as constant. So we have got sine of this. Okay, so that's why integration of sine, that's going to be minus cos. So here we're going to write minus k lambda. So here you see, I will explain it later. Okay, we're gonna get instead of sine we're gonna get cos, and there will be a minus sign which is written before the k, then small t by capital T minus r by lambda, then minus z sine theta by lambda. So here you see this is a function of function. This is again function of z. So we know that integration of sine mx dx, if we have this kind of integration a to b suppose limit, so then we used to put cos mx, then this must be divided by the m again, right? Then we used to put upper limit, lower limit, right? So similarly here the m is nothing but this sine theta by lambda. So here m, we used to take here reciprocal of m, that's why m is taken here. That means 1 by m, right? Okay, so that's why here we can write k, this lambda should be written here, okay, then sine theta should be written below. That's what we have got. So it's very simple integration. Then we have another constant 2 pi that should be written here, 2 pi. Okay, hope you have understood this. Because you see, suppose when you have a constant with this x, sine of m of x, then integration of sine of m of x is minus cos of mx divided by m, right? Similarly, same thing we have done, 2 pi sine theta by lambda, that should be considered as m here in this case. So hope you have understood this. Now let's simplify. So here I forgot to put the limit here, this minus a by 2, this is plus a by 2, right? Now first let us replace this z by upper limit. Okay, then what we're gonna get, let me copy this. Okay, so let's put the upper and lower limits. So here you see this z will be replaced by the upper limit plus a by 2, right? Then minus again, now we're gonna put the lower limit. Sorry, not enough space, just give me a second, just wait. Okay, just wait. So here z is replaced by upper limit a by 2 sine theta divided by lambda minus again cos 2 pi into t by capital T minus r by lambda. Then now this upper limit will be replaced by this z will be replaced by the lower limit, that is minus a by 2. So here let's put minus a by 2 sine theta divided by lambda. That's what we have got, right? Hope you have understood this. So now what we can do here, just give me a second, right? I think there is a mistake. This minus, after simplification, this minus should be plus. Okay, it is plus, right? So when you simplify this term, we have minus here. If you write minus r by lambda, then again minus z sine theta by lambda, this minus and this minus, it becomes plus, right? Hope you have understood this. So that's why this sign is also plus, this supposed to be plus, and this supposed to be plus, and due to this minus, at the end we're gonna get here minus, right? Hope you have understood this. Now here we're gonna apply a trigonometric identity. Okay, let me copy this last step and let me take a new slide to simplify this. Just wait. So here is the last step. This is nothing but y. Okay, so now let's simplify this. So here we're gonna use a trigonometric identity that is equal to cos A minus cos B, which is equal to minus 2 sine a plus b by 2 sine a minus b by 2, right? So consider this one as a and this part as b, and this is sine a and sine b. So then what we're gonna get if we simplify this, then we're gonna end up getting, just give me a second, just wait, because of this minus will be plus, right? And then if we are applying this identity, trigonometric identity, so we're gonna get this result. Let me write here. That's gonna be equal to k pi. These 2 will be cancelled with the 2 that gonna appear after applying that identity. Here we're gonna get pi sine theta sine 2 pi t minus t by capital T minus r by lambda, and sine pi a sine theta by lambda, right? This is what we have got. So now you see, let me explain it again. So take this cos 2 pi this as cos a and cos this as cos b. Then if you apply cos a minus b formula, it should be equal to minus 2 sine a plus b by 2 into sine a minus b by 2. Here you see this minus and this minus becomes plus, and this 2 will cancel this one, okay? That's why we have got this result. So hope you have understood this, and just let me clear this, just give me a second, okay? So that's what we have got, right? Now let us consider that this part, let us consider this part is equal to, suppose alpha. Let pi a sine theta by lambda is equal to, suppose, alpha, and then we can write this equation in this form. Therefore y is equal to ka, so ka sine alpha by alpha, okay? So this part is replaced by alpha, right? And here you see, if you multiply a and a here, then we can replace this part by 1 by alpha, right? This is nothing but reciprocal of this, okay? So that's why here we're gonna get alpha here. That alpha is written here now, you can see, right? Hope you have understood this, okay? This is replaced by alpha, that's why we have got sine alpha here, and the alpha that replaces this term, that a by a replace this term, this 1 by alpha, so this 1 by alpha comes here, okay, right? Hope you have understood this. So this is very simple simplification that you should understand that, right? So then the remaining part is this, let me copy this. So here is the remaining part, okay? This part is written here, right? Hope you have understood this. Now let it be equation number. What was the last equation number I have written? So last equation number was 5, so let's write it. So let's write it 6, okay? This is equation number 6. Now from this equation here we can see that amplitude at this point p dash, okay, this is the resultant amplitude, that's gonna give you a, okay, that's gonna give you a resultant amplitude, okay? So if you let me copy this equation number 6, and here is the last step we have got. Therefore the amplitude at p, the amplitude at p dash, not p, actually p dash, is this, that is Ka sine alpha by alpha. So therefore the intensity therefore the intensity at P dash will be given by square of this, okay, K square A square, then sine square alpha by alpha square. Let me explain how. Okay, now you see, this is the resultant amplitude. This part is the resultant amplitude A, right? Now you see here, if this is the resultant amplitude, then this must give you the amplitude. This is suppose A naught. This is the amplitude at P, and this is the resultant amplitude at P dash. Okay, so sine alpha by alpha. Okay, now you see, then intensity at P, we know that intensity is proportional to square of the amplitude. So this is the amplitude at the point P, and intensity at point P I naught will be equal to it gonna be directly proportional to A naught square. And if we write equal, there must be a constant, let it be C A naught square. Then again, the resultant amplitude at P dash, that must be proportional to the amplitude at P, square of the amplitude at P dash, not P actually. The intensity I at P dash must be proportional to the amplitude at the point P dash, resultant amplitude at the point P dash. Then the resultant intensity, if we write equal, we're going to put the same constant A square here, and if we put the value of A square, we're going to get C A naught square sine alpha by alpha, right? Sine alpha by alpha, and this is nothing but your I naught. Okay, this is nothing but your I naught. Okay, so that's what we can say, that this I naught, which is equal to C A naught square, means you can say C K square A square. Okay, so that's why we can write, let me consider this, just wait, we can write I is equal to I naught, we can replace this by I naught. Okay, so I naught sine alpha by alpha, sine square alpha by alpha square. Okay, so hope you have understood this. So now let me clean these things, just wait. So here it can be written as I is equal to I naught sine square alpha square, right? Actually there is supposed to be a constant C. Okay, so that is supposed constant, and this is replaced by I naught, so C is constant, suppose, right? So here we have got that I naught is equal to C K square A square, which is intensity at P, right? So let it be equation number 7. This is suppose equation number 7. Now let me take a new slide, let me copy this equation and let me take a new slide. Okay, here is the equation number 7. You see, this is equation number 7. Now you see, let's find the central maxima. Central maximum for the point P, so let me show you the diagram again. So here is the diagram. So for this point P, this theta will be equal to 0 at this point, right? Okay, if this line is towards P, then this theta must be 0. Okay, so for the point P, theta is equal to 0, hence from this relation you can see, from this relation you can see, if theta is equal to 0, then alpha will be equal to 0, right? Let me copy this relation so that I can explain you. So we have considered alpha is equal to this, right? So if you put theta is equal to 0 here, sin theta 0 will be 0, then alpha will be equal to 0. So here we can write alpha is equal to 0, right? So now you see, for alpha is equal to 0, right, the sine square alpha by alpha, let me as we know that limit alpha tends to 0, sine square alpha by alpha is equal to 1. So hope you know this. This is a standard limit. So the intensity at P, is I is equal to then I naught, that is sine square alpha by alpha, that's going to be equal to I naught. Okay, that's going to be equal to I naught, because this part is going to be 1 for maximum value, for central maximum where theta becomes 1. Okay, so hope you have understood this. So here is the central maximum, right? So hope you have understood this, which is maximum, right? Now directions of secondary maximum are given by the equation. Let me take a new slide. Number 2, secondary maxima. So sine theta, we have already discussed that maximum will be at odd integral of pi by 2 2a actually. Okay, we have already discussed about this at the initial stage of this video, right? So now if we substitute this in this equation here, you see, let me explain one more thing. Here you see this relation where I have written this relation, you can see from this relation what we can say, what is the alpha actually, what does that alpha mean actually. From this relation you can see this is pi. Okay, this pi a sine theta, what was it? Ignore the pi first. What was it? A sine theta is here you see, let me go to the previous slide. Here you can see this a sine theta gives the path difference, right? BL was the path difference. Here you can see the diagram. This BL was the path difference between the waves from A and B, right? Now you see, let me go to the last slide again. We know that the phase difference is equal to 2 pi by lambda into path difference, right? We know this. Now here you see, this is the path difference. Let's put here. Then what we supposed to get? 2 pi by lambda a sine theta. That's what we should get. Now you see this part is your alpha. So what does it mean? This is the phase difference. This is the phase difference, right, between the waves originating from A and B, right? So hope you have understood this. Now you see, let me write all these things in an organized manner. Okay, since we know that phase difference is equal to 2 pi by lambda into path difference therefore here you can see pi by lambda a sine theta sorry, let me write this one first. Pi by lambda sine theta, if we multiply it by 2 by lambda and then again divide it by 2 a sine theta. So what does it means? Okay, so this is the path difference, this is this factor, right? That's this part is nothing but the phase difference, right? This part is nothing but phase difference. So just let me write it properly, just give me a second. Since the path difference between the waves from A and B is nothing but a sine theta, therefore phase difference between the waves from A and B is 2 pi lambda 2 pi by lambda into sine theta. That's what we should get. That is the phase difference, right? So what does it mean? It means that 2 into alpha, this alpha is equal to this one, right, is the phase difference of the waves originating from A and B, right? Hope you have understood this. Okay, now you see, let us put this value here. Okay, if we use this in this equation, what we're gonna get? We're gonna get alpha is equal to pi a by lambda instead of sine theta, what we're gonna put? 2n plus 1 lambda by twice a. That's what we're gonna have, right? So lambda cancels, then we end up getting 2n pi plus 1, 2n pi plus 1, lambda is gone, 2, okay, a also cancel, not only lambda, so here we're gonna get pi by 2, right? Hope you have understood this. Okay, so if we put n is equal to 1, 2, 3 dot dot dot, then we're gonna get alpha is equal to 3 pi by 2, 5 pi by 2, 7 pi by 2, etc. Okay, etc. Right? So these are corresponding, these are respectively first secondary maxima, second secondary maxima, third secondary maxima, right? So hope you have understood this. So these are the values of alpha for which we're gonna get first, second and third, etc. and so on. Are these are the points where we're gonna get the secondary maxima. This is first secondary, and this is second secondary, this is third secondary maxima. So hope you have understood this, right? Now for this value, what gonna be the intensity? Let me copy this is the values of alpha. So what was the equation for intensity we have got? Let me go back to the slide. So here is the equation for resultant intensity, right? So let me paste here. Okay, so now you see, if you put this value, then what you're gonna get? You're gonna get I naught into sine square 3 pi by 2 by 2, sorry, not 2, by 3 pi by 2 by 3 pi by 2. Okay, that's what we're gonna have. And this supposed to be whole square, because sine square by alpha square we can write it whole square, right? So hope you have understood this. So now you see, sine 3 pi by 2 means what you can write? Sine pi plus pi by 2, right? Sine pi plus pi by 2, that's gonna be minus 1, and squaring that you should get plus 1. So this turn out to be pi naught by minus 1 3 pi by 2 whole square. That's going to be equal to 4 by 9 I naught, and there must be pi. Okay, so hope you have understood this. Not only pi square, it's supposed to be pi square. Okay, pi square. Okay, if we put the values of pi and if we simplify all these things, then it's supposed to be I naught by 22, right? It is approximately equal to I naught by 22. Similarly, if we put this 5 by 2 for for the second secondary maxima, this is for the first secondary maxima, write it properly. Okay, and for the second secondary maxima, so that's going to be I is equal to, if you put the value of alpha 5 pi by 4, and then if you calculate this, then you're going to get I naught by 61. And similarly for the third secondary maxima, you're going to get I is equal to I naught by I have to calculate that, so I don't want to waste time more, it's already too long. Okay, now if you observe the patterns here, I naught by 22, I naught by 61, this value is lesser than this one, right? So that means with increasing alpha the intensity is decreasing, right? So now let us study the case of secondary minima. Okay, secondary minima, here you see what was the condition for secondary minima. For secondary minima, I have already explained that this path difference A sine theta, that's supposed to be that should be an integral multiple of lambda for two appear dark fringes. Why I have already explained earlier, right? I'm not going to explain it again. Then as we already have got that pi a sine theta by lambda is equal to, sorry, not lambda, yes, lambda is equal to alpha, right? So that's why from here what we can write that we can replace this part by this value. Okay, so therefore what we can write, alpha is equal to pi n lambda by lambda, that's gonna give you n pi. Okay, that's gonna give you n pi. So putting n is equal to 1 2 3 dot dot dot, we're gonna get the values of alpha for which we're gonna get the secondary minima. Okay, let me write here for secondary minima, okay, secondary minima. Okay, then we're gonna get alpha is equal to pi, 2 pi, 3 pi, dot dot dot, so on, right? So now if we substitute these values of alpha in this equation of intensity, so let me copy this. Here you see, if we put the value of alpha here in this relation, we know that sine n pi is equal to 0. Okay, so that's why these are the positions where we're gonna get the dark fringes. Okay, so hope you have understood this. So these are the positions of secondary minima. So hope it is helpful for you. It becomes very long. This topic is very lengthy. Okay, so hope you have no doubt, I think, after watching this video. If you do have any doubt, then please let me know in the comment box. So thank you for watching. See you in the next video. Bye bye.